The lecture will be in English today. Mais comme je suis sympa avec vous, je vous fais la bio en français. Philippe Block est professeur à l'Institut technologique d'architecture de l'ETH de Zurich. Il a étudié l'architecture et la structure, notamment à la VUB en Belgique et au MIT aux États-Unis. Il parle français, mais comme il est très chic, il vient faire la lecture en anglais. Il dirige le groupe de recherche qui s'appelle le Block Research Group à Zurich sur les méthodes d'équilibre et de design et de recherche des formes et fabrication de surfaces courbes. Il travaille essentiellement sur les surfaces à double courbure, sur les shells, les voiles minces et les structures soit continues, soit discontinues. Il va en parler aujourd'hui. Il va vous parler également des projets qu'il développe actuellement à partir de robots et de systèmes industrialisés. Son travail se porte essentiellement sur l'analyse des structures maçonnées avec des éléments en briques, de l'analyse graphique, du form finding et de la fabrication et de la construction de systèmes assistés par ordinateur. Je vous demande de bien vouloir accueillir aujourd'hui Philippe Block. Merci d'être venu.
Thanks for the invitation. Can you hear me? Is it loud? Yeah. All right. I'm excited to be here. Let's see how the Parisian students respond to our work. Digital master builder. So an aspect of that is learning from the past. So you will see that there's a lot of this in there. And then why I called it a very arrogant subtitle, Disruptive Construction Technologies, is because I think I don't only think, I know that our field needs to change how they do things. And so I hope that through my lecture I will give you some inspiration or perhaps some ideas on how we could actually really make a difference in design. Starting here, on the top you see actually the construction site of the concrete dome of the ETH Zurich campus, and on the bottom the only high-rise in Switzerland, the Prime Tower. And you see that clearly things have changed, but also many things seem very, very similar compared to the rest of the world around us is really changing very rapidly. So should we also perhaps not reflect on how we construct, how we build, and should we also change? This is a slide that is being used by many policymakers and academics to also clarify a part of the problem. And so here you see the level of productivity. That means like how efficient are we in actually realizing things. And the construction industry is very stagnant, actually embarrassingly stagnant compared to other industries like manufacturing. And colleagues have explained that there is a one-to-one relationship in the level of productivity with the adoption of digitalization and digitization. So it's clear that in manufacturing, there is a lot of this, a lot of robotic assembly, very fast kind of processes. That is not true in architecture. So that is maybe one first challenge that I want to talk about, and why I want to start here is because UN Habitat has calculated for us that by 2020, we will be 2.6 billion more people on this planet. So we will be 10 billion people on this planet. And why is that an issue with respect to productivity? Is that means that we need to really start to provide housing infrastructure for all these people that are still to come. This is a huge, huge challenge. And the way we build now, we can just not get there. We are not efficient enough, not fast enough. So that is a first challenge. But I think a bigger challenge is that our industry is responsible for these three things, and these are things that you as designer can directly actually influence. So the first one, We all know, or that is common knowledge, that, okay, cars should be less polluting, we should fly less, we should take the train, whatever, all these measures, solar panels and so on. But what most people don't know, I continuously notice, is that they don't know that our industry, the built environment, the construction industry, is responsible for almost 40% of the man-made greenhouse gases, so the carbon emissions, so the pollution basically, 40%. So that is actually dependent on what kind of analysis or estimation you follow. That is as much or slightly more than the pollution of all transportation altogether. So this comes from the fact that we use materials in an inefficient way and in an irresponsible way. So I heard that Werner Zobeck was here a couple of weeks ago. So do you remember how he described this? Yeah? Did he tell you about the wall around the equator? Do you remember that? So for those of you that were not there, how much material you need to build in order to provide the necessary housing and infrastructure for all these people. One way to explain is that everything that has been built on our planet until now needs to be built again on the same planet, right? And we don't want to take away all our green and so on, so that needs to consolidate and so on. And he calculates that that translates to a wall around the equator of 30 centimeters and 2 kilometers high every year, just to give you a sense what that means. So that is super polluting, and that is one thing that I want to talk about today. The other one is material waste. So we are responsible for almost 1/3 of the global waste, so landfill, so waste that is not being smartly recycled or reused or whatnot. And that has to do both during construction, this waste happens, and then also end of life and concepts that also certainly Werner Zobeck has talked about, circular economy and things like that. But then the last one is the one that really scares me, is that there is also clear indications that we are running out of resources, running out of materials. We are just irresponsibly using materials, scratching the Earth's surface. And so, for example, people are now kind of clarified that in the next 35 to 40 years, we will no longer have the sand that is used in the concrete as we know it today. So this is scary. In 35, 40 years, we will no longer have that material. You might say, yeah, okay, but we are going to build in wood, in timber, and so on. We don't have enough timber, we don't have enough forest, and we don't want to cut all our forest to basically provide all of these needs. So it is a reality that concrete is used in more than 80% of the new buildings because it's the only material that can provide all of these needs so fast. So that is something that we really need to be aware of. So can we do better there as well? So that is my key message, and now I will show you these 4 grand challenges. I will not linger too much on productivity. I will give you a few hints on how we address that. But these 3 topics, I will show through examples how actually we can make a change, we can make a big change. So the first one is pollution. All right. So actually most of the mass and the material use of a building is in its structure. Certainly when you go to multi-story high-rises, or not even the megatall, but almost, so at least 50 to 75% of the mass of a building is there just to keep itself up. So that is very significant. So if you can have more structural geometry, so for example optimized geometry, shell geometry, vaulted geometry, arches and so on, then you can basically reduce the necessary volume, and that is already a first help, right? So if you have a structural geometry, you can do better. As I said, I do believe that you can learn quite a bit from the past. So for example, from these beautiful structures, these are the fan vaults at King's College at University of Cambridge. They have been standing beautifully for more than 500 years. They have a good geometry, a double-curved geometry. They're just big pieces of stone kept together in compression. And actually, if you know the details of these vaults, these stones are only 10 centimeters at mid-span and 15 centimeters for a 13-meter span, so 1 tree, so almost like this room or a little bit bigger. And basically, if you translate or if you calculate what that means, is that these vaults, without any reinforcements, have been happily standing with a proportion as thin as an eggshell. So if you cut an eggshell in two and you calculate the thickness of that shell over the span, it's the same proportionally as these stone vaults. So this is where I want to say, perhaps we have forgotten something, because I promise you that modern engineers would be very nervous having to put their signature under a structure like that, but also how do we discover these good forms? So that is a first thing where I think we should go back to the past. One of the things that is important there is that this structure works not because it's a material problem. Everything we do is about dimensioning, making sure that the structure can take the force, but actually it's a problem of geometry. If it's a stability problem, it's a problem fundamentally of geometry. And that was also the luck of these master builders, because they did all these historic structures centuries before the structural theory that is being used here. In fact, someone that might have sent us in the wrong direction is Navier. Well, in the wrong direction with respect to understanding good structural form. And indeed, these master builders, they used geometrical rules of proportion. They used scale models, so these are actually drawings of plaster models where they understood what works, what doesn't work, and so on. But then one very powerful way to actually discover a compression form, for example, which is necessary for a masonry structure, is the hanging chain. So something that hangs nicely in tension, if you freeze the geometry and you flip it, then it stands in compression for the same loading case. I expect that you know this. This was first mentioned by Robert Hooke in the 1600s, but that is what Gaudi did in his hanging models. That's what Heinz Isler did, and so on and so on. But it's very painful to make these structural models, so people did graphic statics, statique graphique, well, easy translation in French. Very early starts with Varignon, for example. Actually, a quick, out of curiosity, do you guys and girls get graphic statics in your studies? Not anymore. Absolute disaster. Because in graphic statics, rather than taking a geometry, an input geometry, and then designing or telling if it will work or not, in graphic statics, these master builders had indeed a technique where there was a direct relation between the geometry of your form and the forces in it. So these diagrams are actually the equilibrium of the forces, and you can measure the lengths of these elements, and they correspond to the forces in the elements. So that meant, and I like actually the title of this book by Robert Bow. This is an important reference for me because he's one of the key developers of graphic statics. And the title of the book doesn't say anything about graphic statics. It actually says economics of construction. And indeed, you could then look at a structure. So on the top, you always see the geometry of the structure, and this is the force diagram. Without teaching you anything about graphic statics, you see immediately how structures 86 and 88 compare. For the same applied loads, you see here that globally the forces are smaller, and here the forces are bigger because the lengths are longer, right? So while designing, these designers had a way to actually understand what the relationship was between form and force. And yeah, so this you should know, by the way, right? A deeper structure has smaller forces than a more shallow structure. So, but in a more general case, it's very nice to actually do that. So that is what they could do. I translated these ideas in 3D for my PhD, and I'll show you perhaps an example to clarify what you can achieve when you actually understand that relation. Let's do a quick design exercise. We have a circular support, and we want to span space in compression. So I expect that all of you are thinking, a dome with an opening, like the Pantheon, for example. Well, in fact, all of these solutions can span space in compression only. So going from this alien eye situation to this butt shape there on the left, or this Swiss cheese here in the middle, all of these could span in compression. So what's the difference between all these solutions? And so for that, we develop methods that actually designers can explore and understand what they're doing. On top, you will always have the equilibrium form, meaning the compression-only shape. On the middle, this is the layout of forces, and this is the force diagram. So again, how do you read this one? You can just measure all the lengths of these elements, and they correspond to forces in your system. So by playing with the layout of forces and the non-uniform distribution of forces in that system, you can start to explore all these different solutions. And so what's nice there is that, and you will see this at the concluding slide, is that it's graphical, it's geometrical, but it's actually high-level engineering. So for example, here, in order to get a shape that has all these creases and these ribs, you see that you need to locally attract forces and so on. So this is everything that I show. We actually share for free these tools. So this is Rhino Vault. It's being used by many designers. So any big office that you know, no, not any. Most big offices that you know actually would have used Rhino Vault in their design process. And that is because it gives you that learning during construction. Okay, but you can do anything on the computer, right? So digitally, you can generate whatever you want. So we took the 2016 Venice Biennale as an opportunity to actually clarify that our tools can do something that we couldn't do before. So we developed this structure. So it's 16-meter spans. What you're looking at is 399 cut stone pieces. So cut pieces of stone that are kept together only through geometry. So there's no glue, there's no mortar, there's no reinforcement. So this is just loose pieces of stone that are kept together, 60-meter spans and just 5 centimeters in the middle. So coming back to our eggshell, our structure was 1/3 of the thickness everywhere compared to that eggshell. So it was in this historic kind of context. We did the design sketching of finding these geometries with Rhino Vault. Again, this tool that you can all try out after this lecture, obviously. But I also, and this is maybe, I don't have to do that, but I do strongly believe that we cannot replace everything with computation. If you put crap in the computer, for sure crap will come out. So these are actually my first sketches going there. We had only 5 months to realize this project, but as naive academics, we thought, oh, we have this beautifully informed computational process, we can do it, so we're ready. But then one of the first challenges after, basically, what are the 5 months for? For design, engineering, convincing the Italians we were not entirely crazy, fabrication, and construction. So step number 3, convincing the Italians, took a lot of time. They were not convinced that this could be done. And then we had only 1 month left for fabrication. So we did a calculation. This would be typically how you do it. You mill all the stones. And this would have taken, without exaggeration, 2.5 years. So we had only 1 month, so that was like, shit. So then we looked at other techniques, like these big blades, like how you can cut stone. And here, these are these diamond-encrusted wires. So if you use a wire cutter, a hot wire cutter, this is one for adults. It's exactly the same. And these are super efficient and fast techniques to cut stone. So then we thought and we understood all the limitations and opportunities, and how did we reduce from 2.5 years to 1 month? So here are some of the tricks we did, is that the blanks, so the starting pieces of the stones, would be placed and never moved, so that you never waste time with re-referencing, with moving your piece and so on. Second step was with this big blade, we would just cut all the interfaces, and that has directly, you will see later, a result on the geometry. The inside surface, rather than milling it very precisely, we just did with rough cutting, so just a few lines, and then we asked one guy, Hector, to hammer away all the fins so that it would look a little bit the same. I told you that I wanted this to be an entirely dry assembled geometry, and that has had to do because if we would have added mortar or glue or anything, then our engineering colleagues, I'm half an architect and half an engineer, but my engineering side, I know that my colleagues would have said, yeah, but it's because of the mortar that it keeps together, which is stupid anyways as a comment, but so we wanted it to be entirely dry assembled. Why am I showing this in this context? Is that you can do the calculation. Every stone had to be within 0.4 millimeters of tolerance, because otherwise this 3D geometry never comes together. Because if your mistakes or your imprecisions accumulate in one direction, then it locks and it basically doesn't come together anymore. So, so we then developed these profiling tools to shave off these last fractions of a millimeter, and that allowed us to have these 6 millimeter little registration joints. The key reason that we did this was actually to help the masons, so that they would have a registration on where the stone needs to be. But this, of course, also from a structural standpoint helps us, because you have this shear key that basically prevents that any local force would not cause a local sliding of the stone. So we use this for 2 aspects. But then I also like to show these images. So we did this with the Escobedo group, my colleagues out of Texas, and they brought these highly skilled Mexican traditional stonemasons. And it's very clear from these images that none of this would have worked if we just would have translated our things from the lab. It's the people that know stone that really bring it together. And this was implemented both in the algorithms, but also in how we did the process of assembly. So here some images just to clarify this thin sheet of curling stone. So again, I want to emphasize that only geometry is holding this together. So you have this little registration groove, and so there's no glue and no reinforcement. We also aligned the cuts to follow the force flow to make the piece a little bit more legible or educational almost. And of course, we're inspired by shell builders like Heinz Isler, or if you look here, beautiful shapes like Fraiotto and so on. So here, maybe one more point is that you see the unique outside. It has different parts, but that is, of course, because of the fabrication constraint. Because we never flip the piece, it's flat on the outside. Because we cut it with the blade, it is convex in plan, meaning that it could never align. So that is why we have all these different shingles. And then the inside was done with these cuts. I will skip the movie. And now it's basically in boxes, ready to be reassembled. So it was already once assembled in Texas as a test. Then in just 2.5 weeks reassembled here in Venice, and now it is waiting to be assembled for the last time. All right, so the first thing is structural geometry. So the key message there is not necessarily our macho behavior that we could do it 1/3 thinner than anything else before in stone, crazy, awesome, we're cool. No, that was not the message. The message was that if you get the geometry right, structural geometry, you can actually get strength and stability because of the geometry rather than by adding material and by wasting a lot of material. So that's the key message there. The next one, material waste, I will focus mainly on how things are built. And that is where I see a unique opportunity in digital fabrication and particularly computational fabrication. So not just milling things away, but really a new design process where you embed all the fabrication constraints. So what I'm talking about is rather than having these expensive and wasteful formworks, to start to, for example, assemble your shell from very simple arches and then assemble everything without any formwork and stability. So we're designing these kind of things, but I will show you perhaps some more convincing examples. Let's start here. So shells, geometry is awesome. This is a Pringle carrying 500 times its self-weight in a bad loading case. So you can try this at home, this really works. So you see that double curved geometry is good for a structure. You don't see too many beautiful surface structures in concrete, for example, only for unique projects like the Rolex Center in Lausanne, because they need a unique budget. And the unique budget goes to this, to the foundation, to all this scaffolding, to all this formwork that you need to make. This formwork takes you months and months of milling, of custom carpentry, and so on, and it will turn into this after 28 days after you cast the concrete, because it's a one-off and it will not be reused. There's smart people like Candela that, of course, used parts of HiPars to have a straight line supporting surfaces so that you could reuse many of these elements, but you see that you still need the foundation, a lot of scaffolding, and a lot of labor on site indeed. So we developed a formwork system going onto this fabric formwork, so a fabric with a cable net. The cable net is the false work, meaning it supports the wet concrete, and the fabric is what you can apply the concrete onto. So we explored this first, as always, in smaller things. On the left was my PhD student at the time, Diederik, and I still cannot believe that the client believed that we could do this at a big scale based on this small model. So then they said, okay, go do it in this building. This is an experimental building close to Zurich, and our unit will be there on the top. It will look something like that, which actually excites me because my Swiss colleague like very straight boxes and lines and so on, so this is gonna be annoying to them, like to a crazy extent, so that's great. But that's not the point. The point is more how these structures were built. So here we're demonstrating at quite a large scale. We're talking about 10 meters by 20 meters by 7.5 meters of bounding box for this thin concrete shell. And this will be built on a lightweight cable net that basically doesn't need to be supported from below. So it's not the best application, but it's a first demonstration of what they did. At a certain point, the client indeed got a little bit nervous and said like, you might need to demonstrate that you can do it, and they requested that we did a full-scale, a full-size dress rehearsal prototype of the entire roof. So we teamed up with a construction company. This is Marti. They actually are very traditional, but very respected concrete company in Switzerland, concrete contractors. And we started to assemble the thing in our hall. We developed this kit of parts so that we can quickly assemble it. And indeed, in just 1 week time, a crew of 3 people could basically connect this meccano, this kit of parts. And you might say, that sounds crazy, but please do compare it or imagine the alternative. All this formwork, the foundation, all this milling of something that will be thrown away. So this is a kit of parts that afterwards can be reassembled and used for another structure. I don't know if BIM is important in France. This is BIM in Switzerland, so not very successful. But indeed, so in just 1 week, this thing came together, and I like this money shot because it really clarifies what we're after. So this is what will carry almost 20 tons of concrete. So the cable net weighs 500 kilograms, the fabric 300 kilograms, so with 800 kilograms, we keep the concrete up. And also what's not unimportant is that because this was a one-to-one dress rehearsal, this entire formwork is now in 3 big chunks, will be stitched together very quickly next time, put in place, and in just a couple of hours we can cast the next shell. So here the fabric is being applied. Okay, but what's the trick? Everyone uses wasteful, stiff formwork, and we suddenly say that we can do it with a fraction of the weight, with something that is flexible and lightweight. So what's the trick? A cable net, of course, moves under the weight of the concrete. So we have to pre-stress the cable net such that under the weight, so this is a non-uniform pre-stress, even a pre-stress that is designed such that certain lines are perfectly aligned with the facade, so that we have a beautiful detail, that there where cables come at the facade, it's perfectly straight and so on. So this is what you need to do. So you give it a pre-stress so that it's a little bit too high, so that under the weight of the concrete, it hits exactly the geometry. Pretty smart, right? Has nothing to do with reality, unfortunately, because in reality, there can be any of these nodes, any of these cables can be slightly longer, shorter. You can be certain that over 20 meters, your beams, your edge conditions will be off by a millimeter, a centimeter, it doesn't matter. Your system will respond entirely differently. That's why we developed these nodes, such that we can know where the nodes are, and we scan all the nodes. And so here you see my colleague scanning the nodes. So then what to do? Then we need to retighten so that we redirect it. Oops, next problem. We have about 120 different links, so turnbuckles at the end. That gives you about 90 trillion options. Which is the option that redirects your cable net there? And actually what's pretty cool is that there is people, and this is a nice collaboration in this NCCR digital fabrication. There's people that focus exactly on this, to basically compare an equilibrium model with how your geometry looks in reality, and to from that reduce it to exactly what needs to happen. So now suddenly we have a super lightweight system, but what we need on top is of course a smart brain that helps you basically deal with all this indeterminacy. So here you see another image of the scale, and I like this moment, because believe me, or maybe you see this already, that when I presented this in Switzerland, most construction companies just laughed us away and they said, you're totally crazy, you're a naive academic, nothing is gonna work. This is gonna cost 5 to 10 times more than what you think it should cost. And we're like, no, but we planned everything. So they all laughed us away. Then finally we found Marty. They wanted to do it. Of course, we had to pay a lot for them to do it, but anyways. And then there was a lot of skepticism throughout the process, until this point. Because remember the node, we had this little element that was there to measure all the nodes. So we used this element to basically have all the connectors. And at this point, they started to see, okay, so you planned everything such that this funky shape actually is a very simple shape of 40 by 40 centimeters. And this is where really suddenly there was the understanding of our partners of what digital fabrication, BIM-like processes could do. So here, that's the axis that we use also to attach the reinforcement. In this case, it's carbon fiber reinforcement, because it was something that I didn't say, is that for this big shell, it goes from 3 centimeters to 8 centimeters, so we don't have the typical cover for the concrete. And it would be too difficult to basically pre-bend all these reinforcements. I don't know if you know the project Stuttgart 21 in Stuttgart. I don't know if you've seen it. Then I don't have to make a mean comment about that. But that's what we didn't want. So here then some concrete magic application. In fact, we work together with Lafarge or Lafarge Holcim. Very intense. This now will be slightly different in the new version, because the concrete was a little bit too sensitive, but we did this in one go. Very intense process. It was planned for 16 hours. That's what our concrete experts said, but it ended up being 39 hours. So the workers, that's what they were thinking of our project. Also, what's nice is that we did it in our fancy robotic fabrication lab, but obviously we didn't use any robot to make this. So this is the principle that you can externally pre-stress with this cable net, and then apply the concrete and so on. This is this cable net coming together. It's kind of nice because it looks like a true physical prototyping at full scale, like a physical form finding. So these are things that we will also optimize how we make the fabric. So the edge condition you can be critical about. That was a very pragmatic solution because of all the risk that we were already taking with introducing a new system. Imagine that if this really becomes a product, then you could use just entirely reusable scaffolding on the outside. So this was quite some crazy concrete. You could even vibrate it vertically and it would not come off. So then here the decentering and so on. All right, so maybe another thing that you notice is that this is not quite up to Swiss architectural concrete standards. So there it's a little bit patchy. But because we did this with our industry partners, they know exactly what happened. And it's they, with their reputation, that signed the contract to the client and said the next one will be perfect. So that's actually very nice about doing research hand in hand with industry, of course. Okay, so here, we showed that. Unfortunately, next time we'll do it on top of a building, so there will be some new challenges there as well. This is actually a quote of one of our partners that we use BIM on steroids. More specifically, we use Compass, which is an open source framework, which we again share with anyone. So if you want to do any, things like we do, then you can find all the algorithms there. And the idea of Compass is basically that unlike BIM, that you don't lose or have all these data losses and things like that. And it was the framework that allowed us to interface with all these different partners and things like that. So that means that our new algorithms could directly be used in Rhino or in Blender, or the same geometry is fabrication geometry, FE geometry, all the different things and so on. All right, so one thing that you maybe noticed is that on site we had a lot of logistics. So a lot of different steps, a lot of different things, and that is typically a bottleneck. That is where things can go wrong, where things can get out of hand, where you can lose control, where things can get expensive. So we thought, can we do better? And that's where we started research in 3D knitting of technical textiles. So knitting, it's like to make jackets and Nike fly knits and stuff like that. So literally knitting. Why I start with this little model is because in knitting, 3D knitting, you can generate a geometry like that one and comes out of the machine in one go rather than needing all these cutting patterns. What's special about this geometry, it's like a Möbius strip. It actually folds on top of each other, so it's a non-orientable surface. And again, without needing any stitches, this comes out of the machine. So for that, my PhD student Mariana had to go all the way to how these loops are being made, to then basically generate a fully automated computational process that spits out this knitting pattern for your machine. So in order, because these are non-developable surfaces, right? So that is why you need cutting patterns to cut it into strips that are developable, so that you can lay flat, and then you stitch them together to make a 3D geometry. If you don't do that, then you need to have these kind of shorter rows, and you need to start to change your knitting pattern so that you can drape your geometry in 3D. This is where it gets fun. A very early prototype there on the left, and then on the right, Mariana just dipped this in one of the special cement mixes of one of our colleagues, Lex Reiter in Robert Flatt's group. And then suddenly she had this super lightweight, bespoke complex piece. So you have, for example, a complex node in 3D, and rather than having to make a complex formwork, you have something that is stiff enough but super lightweight that you can replace on site. To show some other potential, we made this little 2-meter span bridge. It's not a real bridge, but a mini one. And to show some other aspects that you can do in knitting, so also this comes out of the knitting machine in one go, so you can have some channels to include splines or cables or reference points and so on. So we made this little prototype. Super lightweight, easy to assemble, and basically what you see here, this weighs 1.2 kilograms and will carry all the concrete for this little bridge. So here you see how lightweight it is. The knit itself is only 400 grams. So imagine how light that is, and that is what you need to shape this structure. So then we add this cement paste, and basically this is another application of strength through geometry. You see that we have a nice corrugated kind of shape. So with just a few millimeters of cement, you can make this into a structural form and apply the concrete on top. So we left it exposed to show that it was unique, and this is happy Mariana and Lex doing dynamic load tests on their little bridge. If you cannot get strength through geometry, for example corrugation or double curvature and so on, then you can actually also add stiffeners and ribs. And again, to me, because you seem not impressed, but to me this is absolutely crazy that something, so a surface with stiffeners in 2 directions, comes out of a simple knitting machine in one process. So this to me is very exciting and has a lot of possibilities, but for that of course you need these computational processes to do that. So Mariana did all her prototypes on this machine as a demonstrator. This was a machine from the 90s. It's a brother machine that is made for grandmothers to make kind of sweaters and stuff like that. So she pulled out the brain, she put in an Arduino, and then she controlled it and she programmed it. But we somehow had the feeling that we could do better. So can we really go on site and do something as big as the HiLo with a formwork that fits in a backpack? So is that possible? So for that, we gave Mariana a new knitting machine. So this is a professional, fully customized knitting machine. And 2 weeks later, we had an opportunity to build a project in Mexico City. We did basically the design, engineering, and fabrication for a project that we, for Zara did Architects. So again, here is Mariana with her backpack. Can we design a shell? So we designed a shell of almost 6 by 6 meters, 4 meters high, almost 50 square meters of concrete surface, so around 5 tons of concrete. And the only thing we needed is 30 kilograms of cable net and 25 kilograms of knit, so basically of sweater. All right, so let's go. So we started knitting, trying to make sure that everything we knit nicely fit together. So this is basically one big scarf that Mariana and Lex put in vacuum form and then carried to Mexico in a suitcase. So here they are. Then they arrive in Mexico City in the museum, MUAC, sorry. Here you see that we try to push the limits. On the inside, we wanted to show that you can actually give a new texture to concrete, so it is a nice aesthetic texture. And on the outside, we have a technical layer that has all kinds of pockets and registration marks. So I will tell you that later. So here it is. Students are helping. As always, students are the cheapest labor one can find, so this is great. And then here you see how lightweight and how easily it can be put. We developed these little edge conditions so that you would have a clean edge for the concrete surface. And then here it is tightened. You see how you can look through it. So it is only 55 kilograms that will carry 5 tons of wet concrete. And one of the things that we wanted to show is that we didn't want to make this shell too heavy. So it was becoming a waffle shell with stiffeners in 2 directions. So we have a 3 centimeter shell with then ribs in 2 directions of 4 centimeters. But that is super complicated to make, super expensive to make. So basically, we use these little balloons, these little modeling balloons, like to make animals, and clowns use those, right? So we use those to make these little pockets so that we would have a nice formwork that has ribs and then a continuous shell on top. So again, this is one part of the technology. Then we add the stiffening paste, and then after this is then just strong enough to apply regular concrete. So this looks like Swiss chocolate, so it must be good. Of course, all of you know that the Belgian chocolate is better, but anyway, it's... or French, I guess. That's hard. So my joke might be annoying in both directions. I say. Typically, I only annoy the Swiss with it, but now you're like, hey, wait a second. We're better than all of you. Yeah. All right, this was before the opening, and so here this shell was then opened. Let's maybe look quickly at this short video. So we left the knit exposed on the inside to really show that it was built in a unique way. The pattern was designed by Zara did Architects to be Mexico-like, and but then all the other things we did, because it's structurally informed. That is also a big lesson, that if you want to innovate, you cannot decouple the architect's sketch from the optimization and fabrication and engineering. But here you see basically the big scarf being rolled and then brought on site indeed. What was also nice about the project is that why I said yes to do this in just 2 months, so from design to installation was 2 months altogether, and was because I've worked with these Mexican craft people before, workers before, and I knew that if we would provide a sophisticated but stiff enough formwork that they could finish it by hand really perfectly. And that is actually also a nice aspect I find, is that it's really a lightweight, efficient system to bring on site, and then you can really bring the crafts to another level. So you can count also on the local craftsmanship to actually make them something unique that comes together. So again, but except for I do think it's beautiful, I do want to emphasize that what we achieved here is basically a way of shaping a structural geometry without any waste or unique aesthetic, and basically logistically simplified to the extreme almost. And the other thing, what's interesting, I said that this only took 2.5 months. So that is very fast. You can really think differently about design, but what I didn't say is that the knitting of the entire formwork took only 36 hours and cost only 200 francs. Swiss francs, so 200 euros, right? So this is also a benefit. It's not only light, efficient, waste-free, but it's super, super cheap. And the next thing we want to do is also to include all the reinforcements, so that in your lightweight package, you also have all the reinforcements included indeed. Okay, last step, resource depletion. So I told you that we are using our materials, and there the trick is, rather than, so the first step is to reduce the structural volume. So if you have a shell, then you can reduce the volume. But if you, within the language or the group of good geometries, if you have compression geometries, you not only have thin geometry, so funicular means compression only, like voûte, like arches and vaults and so on, but then also the stresses are very low. And so that means that you basically can use very weak materials or materials that are fully recycled and so on. For that, we again go to the past. I don't know if you recognize this structure. This is in New York City. It's in Grand Central Terminal. It's the Oyster Bar. This was done in Catalan vaulting, so built with a lightweight tile in stable sections. So when you go next time in New York and you look at this is not decoration. This is actually one of 3 layers of unreinforced masonry. And it was built without any scaffolding and formwork from below. So I show you this extremely old project that I was lucky to do with Peter Rich and John Ochsendorf in South Africa, because this project really opened my eyes. This really made me understand why one should care about geometry. So it was a very remote location, and it was useful to actually not bring in a lot of engineered materials. So can you do as much as possible with local resources, both material and labor? So we activated 12 people to press these tiles with just a little bit of cement, and then we taught them how to build this new technique. And so once you have these boundary conditions, so you have the boundary arches, then you can start to build in stable sections. So all this wood that you see there would be reused for the different elements. It's not formwork, but it's actually guide work, because we are using farmers and carpenters, and it was important, of course, to give them the geometry. A professional mason doesn't need any of this help. So here, very simple results, but why I'm showing you this project is because of this slide. So here, this is an anecdote that I heard from one of the master builders, James Bellamy. He said that, I said like, oh, how great that everyone was engaged. And he's like, no, you don't understand. This was week 2, because week 1 was a total disaster. Why? So these tiles are 25 centimeters, and they're designed to only take 2 megapascals in compression. Do you know what that means, 2 megapascals in compression? Like 10 to 15 times less than the most regular concrete we use. So basically peanuts in compression. But then even better, if you take this tile of 25 centimeters and you hold it on one end, it breaks in bending. It has no bending capacity whatsoever. And that is why the women are carefully and happily carrying 3 tiles at a time, because the first week, more than half of the tiles arrived on site broken because the men couldn't be bothered. And so basically everything arrived broken. But, and this is the message, tiles that are so weak, if you place them where the forces want to go, as an arch with a tension tie, then it's stable enough to basically carry the worker on top to build up a safe floor in a multi-story building, right? So, I don't know, this to me was absolutely mind-blowing. This tile was so weak, honestly, if you take this tile, it breaks in front of you, but if you place it where the forces want to go, you can activate it as a structural material. That works, of course, because an arch is a good geometry, but not for point load, so you add stiffeners. And then what's very important, the curved geometry is not enough. You need to control the boundary conditions. You add a tension tie. And what we just did, something that everyone did 150 years ago, building little arches in basements and everywhere. We saw arches everywhere. No one knows how to design those anymore, but what we now just did is we basically made a super lightweight version of a beam, just by reintroducing the arch, by adding stiffeners to take the live loads, by adding a tension tie to make it an independent element and not have the thrust on the neighbors and so on. And actually, if you calculate this, we just saved 70% of material if you take this into, for example, a floor plate. So by reintroducing the arch, so we haven't talked yet about optimization and computation and so on, you save more than 70% of material. So that, of course, helps to try to help people in such a context, but I will show you how that can have a bigger impact in our context indeed. Okay, so I often work together with Dirk Hebel. He's a colleague of mine in Karlsruhe, and he likes to challenge me. So in Africa, you have a lot of labor and soil and smiles available. What do you have available in New York is a lot of waste. So can we, like our buddy Wally, compact waste and start to build structures in waste? So he found this very weak material for me. This is compressed Tetra Pak. And it has 1/10 of the compressive strength of timber, okay, whatever, but 1/100 of the elasticity modulus. That means that it's super flexible, it's not a structural material. So that, of course, gets me excited. Can we do something with a non-structural material? So we built this pavilion in New York. Of course, it's an arch. And so you basically can just compress this Tetra Pak and make little plates out of it. But because we use this masonry logic, we could actually pre-assemble everything in lightweight pieces that could then be assembled without any glue, nails, anything, because this pavilion would only be there for 3 days, and then we wanted to re-shred it and basically leave no footprint whatsoever. So here everything is being assembled, and then again, this allowed us, because of masonry, we didn't need complex connections on site. This could then again be achieved with the cheapest labor available, as you now already know, students. So here, this was then a little bit of fun. So this is orange juice, this is milk, and oh, let's go back. This will work here as a joke. Oh no, where is it? The other side was entirely black from the other side, because in the US they drink wine out of carton. So there was black from one side and then colorful from the other side. So there it was, a nice little cathedral of waste in New York. Dirk Hebel asked, like, I have an even more stupid material. Let's do something in mushroom. So this is grown mushroom. Have you heard about this? So you can grow mushroom and bricks and so on. This has 0.2 megapascals in compression. So remember, 2 megapascals was peanuts, so this is 10 times less than peanuts. So absolutely stupid of a material. I was annoyed that everyone called me the arch guy, so we wanted to show a 3D structure that is like an arch in pure compression. And so this was standing there, so it's about 3.5 by 3.5 meters and 2.5 meters high. This is a tree structure out of mushroom that stood in Seoul, Korea for 1 year. It surprises me, it was only there for half a year, or meant to be there for half a year, but they liked it, and so they kept it longer. It smells really funky, so I'm not sure why. So anyway, but the key point there is again, so there the key point is that if you from the efficient geometries actually stick to compression geometries, then suddenly you can start to use not only cheap local material or recycled material or even grown material. So suddenly non-structural materials become structural. And so let me now pull this all together, because I think this will clarify why we're doing what we do. So we already learned that if we go from bending to arch action, you save more than 70% of material. So we designed a floor plate of only 2 centimeters of unreinforced concrete for a 5 by 5 meter floor span. So we did some early prototypes. I don't have time to talk how different this is than, for example, Nervi's floor. It might look like it. Sounds really efficient, right? So here we save more than 70% on a floor. But again, bad news. Because these geometries are complex geometries, you need, for example, this was 2.5 years ago. You needed a very complex double-sided mold to realize this, so this could only work for a model building. You see how wasteful this is. And that is where we already 2.5 years ago gave the hint that actually with new additive manufacturing, like 3D printing, there might be an opportunity to actually, without needing all these molds, to realize this efficient geometry. So this was a 3D printed floor. I will skip this point. And so that nicely came together. So this 3D printed floors, this is sand 3D printing. It's large-scale 3D printing. It was never meant as a structural material either. So actually, it has similar properties to the tiles in Ethiopia. So basically, if you take a piece out, you can snap it as easily as cold dark chocolate. So okay, let's say French chocolate. So if you take it out of the fridge, that piece, you can as easily break it. And it has only roughly, again, 2 megapascals in compression. So we did the entire requested loading regime to actually show that you can take all the loads. And if you don't believe me, this was at the time half of my team. So this is 1,200 kilograms of ETH nerds that are standing on a 2-centimeter floor prototype made out of something equivalent to chocolate, right? So if you think that this is crazy, or if you think that I am very in my own bubble and world and so on, let's maybe look back at this example. So this structure, what I told you is that it's 3 layers of unreinforced masonry. It was built without any formwork, but more importantly, it's actually also carrying the Vanderbilt Hall on top. And the Vanderbilt Hall is one of the 2 main entrances of the train station. So if you think that we are kind of weird and crazy, then certainly 3 to 4 million New Yorkers are risking their lives going to work every single day. So this is also something interesting to me, that actually we have forgotten how to design like this. We have forgotten how to design for constraints, for low material, for very little material, and so on. This ignorance is not new. This happened the entire time. I also don't have time to talk about that. But so I showed that all these funky shells that we have, you can also use them to hide them inside of a floor. So you have a very efficient little shell where typically your massive, for example, concrete floor is. Can you imagine the impact in a high-rise? In a high-rise, I've asked several offices like SOM that do a lot of big high-rises, at least 50% of the weight of the entire building is in the floors. So if you can make the floor 70% lighter, the impact on everything is there. Another opportunity that you have is not just to hit the structural, but is actually to, rather than layering, this is a typical model that you see in Singapore, for example. The average floor depth in Singapore, of Singapore high-rise, is 1.5 meters. Because they don't want to have any clash, so they have mechanical systems, structures, other systems, and so they layer everything like pancakes. So now you can basically start to activate the cavities in between, and you can start to lay in other media and so on. And so basically what that allows you, these kind of ideas, is that not only are you 70% lighter on the floor itself, but also if you reduce this, and we have done the exercise, in Singapore, for example, you would get 1 floor for free every 2 floors. So that's a lot of real estate. So that means that your client is happy and everyone needs it. I don't have time to talk about acoustics, but there's also good news there. Rather than in lightweight structures adding a lot of weight, you can actually again use structural stiffness to make your floor as efficient in transmission noises as adding the weights. And the same as what is relevant in optimization of geometry. For structural, is that shape is most important, then topology, meaning the stiffness, the layout of your stiffness, and only then size. And knowing that almost, let's say 95% of our engineering colleagues only do sizing, they should actually maybe also start looking at shape. We should give them the tools to look at shape, and we should as designer all look at that. So I want to close with this image, because this image brings everything together for me. It reduces the mass. So we are more than 70% less material. So that means that we are polluting significantly less. We use state-of-the-art digital fabrication to realize this structural geometry, But this was a floor that carried my entire team, half of the team in fact, at the time, a material that is so weak that basically we can tell our material science colleagues to not always go for more megapascal, more strength of material, like ultra high performance concrete, ultra this and so on. No, because they're super polluting materials. Actually, if you get the geometry right, you find a clever way to realize your geometry, you can use entirely recycled, grown, weak materials that have no embodied energy or even absorb carbon as a structural material. So for me, this is an important metaphor, and I'm excited to say that we are actually commercializing this floor. So in the next 2 to 3 years, you will in your designs be able to replace a floor by something that is 70% lighter and built with predominantly recycled materials. All of this is only relevant if we all start sharing, because these grand challenges are so big. That is why we develop things like Compass, so that we start to learn from each other and not all of us reinvent the wheel and basically go towards a planet that will no longer be there sooner rather than later. All right, that's it. Thank you.
Thank you, Philippe. On va passer aux questions. Y a-t-il des questions pour Philippe Block?
First of all, thanks, because it's very, very impressive. So you present in the last part. You told us that you used 3D printers, but they also create plastics. So did you thought about the way of reuse the plastics in the 3D printers?
Yeah. Sorry, I was running out of time and I saw many people fall asleep, so I was trying to go a bit faster. So I skipped a few details, but this is sand printing. But what's nice is I might be contradicting myself. So you say sand, but we're running out of sand. This is actually the sand we're not running out of. So it's desert sand and so on with a simple binder. So it's binder jet printing. But it's a very specific type of printing. So here actually it's not that important, but you make another good point is that if you use, for example, plastics for formworks, there's a lot of biodegradable and reusable whatever kind of plastics. So I think in everything it's important to try to do the best you can with what's available now. What's neat here is that, I mean, we get to a meaningful size already, and it gives you an outlook. So, for example, for the moment, this 3D printer uses quite toxic materials. But it's actually a no-brainer, and there is already other products out there that use less toxic binders and so on. So in this one, it's actually directly 3D printed. So it's not cast inside of a 3D printed mold. But that we are also exploring, and there you can certainly there must be some elegant or ways to also address the plastics and things like that. Yeah.
Autre question.
Ici.
I want to thank you for the presentation. My question was about the netting project. Well, basically, when you were talking about the other project which used the same technology, you've used digital technology to measure the difference that will happen when we add the weight. Well, with the netting one, how were you sure that the difference wouldn't make a problem?
Yeah, great. We're doing exactly the same. So, in fact, the patterns on the inside can also be easily scanned and give us a reference so that we can retighten. But so with the knit, we're much earlier in the knitting research because their division actually, and I am pretty sure that that we will realize it in 3-4 years, is, for example, to have something that is bundled in a thing like an igloo, and you fly with a helicopter or whatever, you drop it, and by the time it lands, it's entirely self-deployed and then stiffened, and then drones come in and spray it, and so on and so on. So that we will show in three years. I mean, I can promise you already. But what I'm trying to say there is that what we did with the knitting here is that we fell back on something that we knew. We used the cable net to actually know exactly where the geometry is, and then the knit is only there to drape, to give you the pockets. So the knit topology is such that it inflates only until where we want it, and so on. But the outlook for me is to do everything with the knit and no longer to have to mix with the cable net and the fabric. But then to answer specifically your question, is that this pavilion is small enough and is by itself. So why we have to solve it for the other one is because, and I forgot to say that, with this control algorithm, and we tightened it, we went from 8 centimeters of deviation of the target to just 1 centimeter, which is well within the expected tolerances for concrete construction. And there we have to do it because there will be glass facades. It becomes a building. In this one, it was a fast-paced demonstrator. We didn't need to do it, but the same principles apply. So we, because in the knit, we still had a cable net. So it's the same algorithms, it's the same ideas and so on. But in general, it's a challenge indeed. That is also why everyone uses stiff formworks. Very wasteful formworks, but stiff because you know exactly where the geometry is and you don't need these additional algorithms. And we are trying to scale things up to really demonstrate that the exciting things at small scale have a potential at large scale, but only when you add these kind of logics. So, so there's two parts to two answers to your question. Is that yes, that also needs to happen, but because this one was smaller, and because it didn't have any interfaces with facades and things like that, it was not that important for this one. Because the pavilion had so much double curvature anyways, is that if you're off a little bit, it doesn't matter. It's the same pavilion. It's equally safe. It's, yeah.
Just a follow-up question. When you say algorithm, does that mean when we have a part that is off a little bit, and if you want to modify this part, would that affect the other parts or not?
Yeah. That's a big part of the challenge, is that the entire system is dependent and flexible, and so you indeed need to find a combination of global actions that solve your problem locally, but don't make all the rest worse, right? And that's why it's actually complicated. I only focused on the 90 trillion combinations. But what's complicated there is that which of these combinations actually address a local problem in a global kind of control way. And, but it's nice, that's why I recommend to work together with people in very different fields, because there is a lot of smart people that suddenly can help us make big differences. And so that's exciting. Yeah.
Y a-t-il d'autres questions? Yes.
Yeah.
Thanks for the presentation. I have a question also on the lightweight formwork.
Mm-hmm.
You put all the digital fabrication and control on the nodes of the formwork.
Yep.
And I would like to know how you can control the workers that are projecting all the concrete, and how you control the thickness of the shell.
Yeah. Okay. That is also something that initially we thought we needed all kinds of sophisticated things, but actually I also made a comment about digital versus crafts and versus understanding what people actually in practice do. And so you had this reference mark every 40 centimeters, and actually they don't even need 40 centimeters to be able to, it's like a mètre du plâtre. You need just a few reference marks, so all of these have the right height, and they can easily interpolate in between. So that's also something that we grew to learn, that if you try to replace everything digitally, either you need to develop all these kind of smart algorithms and things like that for measuring while you're spraying and so on, while actually someone that does concrete works every day or finishes and so on doesn't need any of that. And so I think also it is very important to acknowledge that and to understand these opportunities, that not everything needs to be kind of controlled digitally, because here these reference marks are plenty enough. And so that's kind of interesting, I find. Yeah. So you enhance the possibilities. In our case, we enhance the possibilities. I want to re-emphasize this, right? Not just because of adding and maybe giving a new aesthetic, but really because we care about structural geometry. We are realizing a large structure with very, very thin sections, right?
One more question.
I was very curious about your stone project.
Okay.
Yeah. You said that it was standing only by geometry, and we all know and it was supposed to be rebuilt, and we all know this IKEA problem when you dismantle something and then you have to rebuild it, kind of altered, and it's stone.
Yeah.
How does it work?
Actually, you don't. Maybe you see it. Actually, it's. You see there the corners are broken off and so on. So the more you rebuild it, the more indeed you will have all these chips and all this and so on. But I don't know exactly what you're asking, because actually what's quite nice is that this came out. You could take it apart much easier than together. What you basically did is you place all the supports from below. Then you tighten the reinforcement so that it basically lifts a little bit. You take a stone out, and then you just one stone after the other could easily take it again. And maybe one thing that maybe another aspect to the IKEA part, what I didn't tell because I was rushing, is that there is the last row of stones, like the keystone. Of course, you have in every other stone you have these registration marks, but the last one, if you have these little registration grooves, it doesn't fit. So the last one is blank, blank. So just slides in and locks it. And so that is also the one that you want to pop out first, and then the other ones can just be peeled off one after the other. But that actually, maybe I'll misuse your question entirely to make another comment, is that the logic of masonry, so not necessarily to make vaults and stuff like that, but we also, and I didn't show you that, we're also using, for example, the masonry model and logic to discretize a frame structure or a box into pieces that can be assembled without needing very complicated connections. So they're just touching, not sliding, simply interlocking. And so that is, of course, a key, that this is nicely kept together in equilibrium, but also it doesn't need glue that needs to be dissolved or that needs to be untightened or cut and so on and so on. So that is something that we did there. I don't know if I answered your question.
You answered.
Okay, good.
Okay, thank you, Philippe. It was a great lecture. We were very proud of that you came here, and it's exactly what we're trying to teach here, to reverse the fact that we are not beginning by drawing and then building, but thinking of the material and using it.
Perfect, yeah.
For the project.
Maybe do consider graphic statics, I would say.
Yeah, no, I do. The graphic static is very important.
Yeah.
And do you know Mayer?
Who? Mayer, no.
He's the guy in the 19th century that developed a static graphic in 3D-dimensional.
Okay, yes.
I will let you know that.
Yes, please.
It was very exciting because it did volts like that,
yeah.
And you can see the measures of the forces.
Actually, just a quick side comment to that. It's absolutely mind-blowing that you always think like, okay, now I really know everything about a topic, and then you go to a place that has another language, and there's so many references that are not known in the rest of the world. So I'm sure that the French already did all of this at some point.
But he tried to
Mayer.
To use the static graphic in 3D, which is quite complicated by hand.
Yeah.
But now I'm sure we can use it by computer now.
Exactly, yeah. So the tree structure was designed with 3D graphic statics. And that's also available now if you want a true compass. In December, it will be available. Full 3D graphic statics.
Non, mais la statique graphique a un vrai avantage, c'est parce que ça permet de donner la relation directe entre la mesure des forces et la géométrie. Et il suffit d'avoir un ensemble de forces fermées pour que le système soit en équilibre. Thank you so much, Mr. Block. Yeah!